All right. Binary compounds. How do you name binary compounds? When you're naming binary compounds, well, like I say, the thing to remember, first of all, is that binary does not mean diatomic. When I'm talking about, I have lone atoms and I have molecules. I also have ions. When I'm naming molecules and ions, diatomic means two atoms, like Br2 or CO, or that that mercury ion Hg2 2+. Those are all diatomic. Binary means made up of two elements. It means that whether I'm talking about methane, CH4, water, H2O, it means there's two flavors of atom involved in that molecule. And you can have binary ions too. You can have CL02 1-. You can put a charge on a chunk of more than one as well, and you can have binary ions as well. All right, these terms, triatomic, diatomic, binary, you're going to need to get comfortable with those. Okay, so how do we form binary compounds? We alluded to this earlier, right? If you get two charged species, they'll snap together, nice and clean. Remember, the metals, which make up the bulk of the periodic table, everything under that little staircase, starting with boron and going to the right for 7 elements, except aluminum. We write the staircase and we leave out aluminum, which is a metal. Everything to the left of that is a metal. The majority of elements on the periodic table are a metal. Somebody asks you on a test, if I pick one element at random, what is it most likely to be? The answer is it's a metal. Most of the stuff is a metal. Now, the stuff in the upper right-hand corner, though, above that staircase, those are nonmetals. And when I bring, and unlike metals, which lose their electrons very easily, they don't want to give them up. Nobody wants to give up an electron. But nonmetals are aggressive about taking electrons, except hydrogen, which is a wild card. Hydrogen is absolutely a non-metal, even though on the periodic table we write it over with the metals. Hydrogen is a non-metal. And then that little staircase in between, with the exception of aluminum, which is definitely a metal. But if you start at boron and go one down, one over, one down, one over, one down, one over, those 7 elements are called metalloids. And they're kind of the gray space between the metals and the non-metals. They're sort of metals. All the properties you associate with metals, they're sort of that. They're halfway to that. They are somewhat malleable, somewhat ductile, some decent conductors of heat, and they are semiconductors of electricity. You should be able to identify the 7 metalloids on the periodic table. All right. So when we talk about metals and nonmetals, this is the starting point of forming binary compounds, because the simplest way to form a binary compound is to take an element from each side. Lithium from one side of the periodic table, a metal, chlorine from another. Bring them together, and when I do, one is going to rip the electron literally off the other. You see which way the electrons are going to go? Again, metals lose their electrons. Non-metals are more likely to grab them. Chlorine is a bully. He's going to rip that electron clean off of lithium. And now I got 2 charged particles, a plus and a minus. You have 2 charged particles, they snap together. They form these big arrays. And the name is formed the same way. I take the name of each particle, the lithium ion, the chloride ion, snap it together. Don't make sure you take off the words ion on the end when you do it. And the substance that is a result of lithium ion and chloride ion coming together, that's lithium chloride. All right, now a couple tricks here. One is always lead with the positive. Whether you're writing the name or you're writing the formula, always put the positive first, the cation first. Lithium, it's always lithium chloride. It's never, for example, chlorine lithide. The cation always goes first in the formula and in the name. So, for example, behind me here, what do you think we'd call that first one? Where I got sodium and bromine together, well, since the cation went first, that's going to be sodium ion. The other one's going to have to be negative. That's bromide ion. Therefore, the name becomes sodium bromide. Again, if I look at that, I've got chlorine and magnesium reacting to form a compound. Magnesium is going to be the cation, goes first, it's the metal, magnesium ion, and the chlorine forms chloride ion. So when I snap that together, that's magnesium chloride. Next one would be potassium and sulfur forming potassium sulfide. Aluminum and fluorine coming together to form aluminum fluoride. Beryllium and nitrogen coming together. Beryllium nitride. Now the next one, HCl, don't get confused on this. This is not an acid, okay? Hydrogen and chlorine coming together form hydrogen chloride. This is one of the substances that makes the binary acids. Binary acids, as you'll find out in a minute, are a mixture. They're not a pure substance. That substance is hydrogen chloride. But hydrogen is a wild card. It can go in front and be the hydrogen ion with the chloride ion to form hydrogen chloride. Other times, it goes on the end, like when it reacts with lithium. Lithium and hydrogen, then that's lithium ion, but hydride ion now. So the name becomes lithium hydride. Hydrogen is a wild card. You can use it either way. Cesium phosphide, sodium carbide, potassium oxide, it follows the same pattern. This is how you get the names of these compounds from their formulas. Now the next question is, well, how do I get the formulas from the names? Because you need to be able to go both ways. All right. If somebody gives you a formula and says, what's the name of this thing? If somebody gives you a formula and says, what is the name of this thing? Look at that iron there, right? Remember, iron can have more than one charge. In order to name it, you are going to need to know which iron ion you are looking at. The trick is the compound will always have a charge of 0. That means the charges have to cancel out. Well, chlorine, for example, always has a -1 charge. It's fixed. It's a representative element. So, for example, if I'm looking at FeCl3, that means in my molecule there are 3 -1s, which means the iron must have had a +3. So for it to be 0 and the chlorine ion be -1, 3 of those means 3-. Iron must be 3+. If I bring those together, then I just need to make sure I name the material either ferric chloride or iron 3 chloride to represent the right charge. Okay, how about on this one? Let's see, we just did the first one. That's ferric chloride. How about the next one? SNS. Now, SN can have more than one charge, but sulfur always has the same charge. Almost always has the same charge. Sulfur is a chalcogen. They form a 2-. That means 10's got to be a 2+. 10 is in that third group of variable elements, either 2 or 4. So 2 is the small one for that. Do you know how to name the small tin ion? 2 is company, 3 is a crowd. 2 is us, stannous sulfide. Or simpler yet, 10-2 sulfide. Chromium and nitrogen, that's chromium is part of the FCC, the first group, iron, cobalt, and chromium. They do 2 or 3. And nitrogen always does a 3. So that means chromium's got a 3+, nitrogen a 3-. The nitride part is easy. Be careful with the chromium, but that's chromium 3 or chromic nitride. The next one, copper and mercury, those are the one-offs. Copper is either a +1 or a +2, but bromine's always a -1. That means copper's got to be a +1. That means it's the small one, cuprous bromide, or said another way, copper 1 bromide. All right, you comfortable with this? I mean, if we got the next one, I've got mercury Hg2F2. Be careful. Remember, mercury is that diatomic ion. Hg2 is actually 2 plus, and it's balanced off by 2 fluorines, each 2 minus. So Hg is 2 plus, but it's plus 1 per atom. So that's the mercury 1 fluoride. Underneath it, it's the mercury 2 fluoride. Then we have, let's see, cobalt. That's the small one, because sulfur is a 2 minus. That must be a 2 plus. Cobalt is 2 or 3. It's the small one. That's the cobaltus, or cobalt 2 sulfide. Magnesium chloride. Magnesium is a representative element. Be careful on that. It looks like manganese. I would have to say manganese 2 chloride, but magnesium, it would be wrong to say that. Magnesium is just magnesium chloride because the charge is predictable. 10, 10,2 sulfide. Again, sulfides are 2 minus. So this time, it's 10 sulfide is 10,4 sulfide, or stannic sulfide. Iron oxide, rust basically. Iron oxide here. Oxygen is predictable as the sun setting. Oxygen is 2 minus, therefore this must be the iron plus 2, the ferrous oxide. All right. Now, how do I find the formulas? How do I go in the other direction? How do I find the formulas? Somebody told me I was making a compound from magnesium and chloride. They told me you're going to work with magnesium chloride. I would just, first of all, figure out what ions I'm working with. Magnesium is 2 plus and chloride is 1 minus. It's got to have a neutral charge. So to find the formula for this, well, I would take a look and I'd say, well, if I have 1 magnesium, I'm going to need 2 chlorides to balance it out, because the magnesium's got a plus 2 charge. To balance it, I need a minus 2. That's 2 chlorides. That means the formula is MgCl2. So these binary compounds made from a metal and a nonmetal, it's really easy to get the formulas. Be careful. Some books will tell you just take the charge of one and make it the subscript of the other. This particular case, it might work, but don't do it that way. Sometimes it won't work for you. Barium is predictable at 2 plus. Phosphide is predictable at 3 minus. The smallest whole number multiple, the least common multiple of those two, is 6. So I'm going to need to build a 6 plus charge and a 6 minus charge to balance it out. So that means to get a 6 plus charge out of barium 2 plus, I'm going to need 3 of those to get a plus 6. Phosphide has got a 3 minus. I'm going to need 2 of those. That means my formula is barium 3, phosphorus 2. Makes sense? And like I said, in this case, if I just took the charge of phosphorus and made the subscript, it would work. The charge of barium made the subscript on phosphorus, it would work. Won't always work. Here's an example. 10 sulfide. If I just swap the charges for the subscripts, I'd end up with 10,2 sulfur 4. That's not the case. The least common multiple here is 4. So I can neutralize the charge with I can get least common multiple 4 with 1 10 and 2 sulfurs. That means my formula is SnS2. Be careful. Don't just swap the charges as suffixes. All right, so this is how we can go through and we can realize beryllium sulfide. Beryllium is a 2 plus, sulfide is a 2 minus. The formula is just snapping those two together. Calcium, you know what the charge is on calcium? Calcium is a 2 plus, chloride's a 1 minus. Bring those together, snap them together, and you get calcium Cl2. Formula CaCl2. Potassium sulfide is K2S, because each potassium is a plus 1, sulfide is a minus 2. Aluminum fluoride. Fluoride is a minus 1. Aluminum is a plus 3. So I'm going to need 3 of those -1s to balance the aluminum. Aluminum, F3. Is this making sense? So far, so good. Okay. All right. Hydrogen or magnesium nitride. What's the charge on magnesium? Careful, manganese and magnesium are different. Magnesium is +2. Nitrogen tends to form a 3-. That's of the pnictogen family. Bring those together, you're going to need 6 on each side. You're going to need 3 of the magnesium and 2 of the nitrogen. Hydrogen chloride's easy. H+, Cl-, slap it together. All right. So there's some more here you can practice. Cesium phosphide is going to be CS3, phosphorus. Calcium carbide is going to be 2 calciums to balance out a 4- on carbon. Although carbon doesn't form these ionic compounds the same way. It tends to form more covalent. We'll talk about those in a minute. But there's some more there to practice. All right, so this is how you're going to name the majority of the compounds you're going to run into. The majority of the compounds you're going to run into include are these binary compounds where you have a metal and a non-metal, or at least something from the left side of the periodic table and something from the right side of the periodic table. But I'm telling you now, you will also run into situations where you have 2 non-metals. 2 things, neither of whom are going to give up their electrons the way a metal does. For example, I can make compounds from nitrogen and oxygen. If I make compounds from nitrogen and oxygen, I bring them together, there will be no ions formed. Both will grab each other's electrons, but nobody's going to give them up. So there are no pluses and minuses. Instead, I form their electrons intermix and I form a covalent bond, a much more interesting kind of bond. All right, but we're going to name these the same way because many of these compounds, they got their names before we even knew what an atom was, much less a charge on there. So what we're going to do is we're going to imagine one of them was an ion and imagine the other one was the opposite ion, and then call it, for example, nitrogen ion, oxide ion, slap the 2 together and name it the same way. Now, the challenge then is figuring out which one is the positive, because remember, the trick is every compound has 1 proper name. And while it might have some other common names, there's 1 proper name. So to figure out the proper name, we got to know which one we're going to treat as the more cation-like thing to start with. There's a long story to this. We're going to keep it simple. Fluorine is the king. The most anion-like thing on the periodic table is fluorine. When you get into a fight with any atom, the one who's going to walk away with the electrons is most likely going to be fluorine. There's not a lot of fluorine in the world. There is a ton of oxygen. He's number 2. He's right next to fluorine. He's very fluorine-ish, very fluorine-like. But fluorine is undoubtedly the king. And the elements close to fluorine tend to be more like fluorine, and the ones as you get farther away are less like fluorine. So if I had to decide which one was going to be the more anion-like, the one that comes second, I'd pick the one closer to fluorine. And the one that is more cation-like, the one that is more likely that should go first, I'd pick the one farther away from fluorine. I'll give you a better trick on this later in the class, but this is a way to get us started. So, for example, if I have the elements nitrogen and oxygen, well, oxygen's right next to fluorine. He's the more anion-like, and nitrogen is farther away. He's the more cation-like, so nitrogen goes first. If I have, for example, the elements oxygen and fluorine, that's not even a challenge. Anytime you have fluorine, fluorine is the anion, flat out, no choice. So it's going to be an oxygen fluoride. If I have chlorine and bromine, or carbon and bromine, okay, carbon and bromine, which one is closer to fluorine? I look on the periodic table, see the one that's closer to fluorine, and that's carbon bromide, not bromine carbide. Choose by how close they are to fluorine. If I have silicon or chlorine, see where silicon is? Chlorine, though, is right under it. That's going to be a silicon chloride. And if I have something like phosphorus or sulfur, sulfur is a little bit closer than phosphorus, so that becomes a phosphorus sulfide. All right, now this is half the challenge when you're dealing with the nonmetals. You got to figure out which one goes first. Always lead with the positive. The second challenge is because we're not forming ions, because there's not an anion and a cation involved, then we can't figure out the ratio of these as cleanly and as easily. And in fact, you can form more than one compound. Now, when it's simple, just do the simple story. Lithium chloride is just lithium chloride. When there is ambiguity, you have to specify, like we did with iron. If there's two irons, you got to say which iron. Okay, when you're dealing with these, there can be way more than two. Phosphorus and chlorine can form like a dozen different compounds. PCl3, PCl5, P2Cl7, all of these are possible. So we have to specify. When you're talking about lithium and chlorine, do not do this. But when you are talking about two nonmetals, you have to specify the atom count. I have to say there are 2 phosphoruses and 7 chlorines. The way I do that is I use the prefixes that you're probably already familiar with from geometry. Mono and di mean 1 and 2, but then after that it's tri like triangle, pent like pentagon, hex like hexagon, oct like octahedral. The prefixes that you're familiar with from geometry, you use those to specify the atom count. The one you got to be careful about is 7, okay? Not 7, not sept, like September or septagon. We use hept. So in chemistry, not sept, hept. But for example, P2Cl7 is diphosphorus heptachloride. Now, there are a couple twists on that. One is, remember, if there's only a single atom, use mon. Into O is going to be dinitrogen monoxide, not monooxide. When you use when the prefix and the suffix, or when the prefix and the element, when the prefix ends in a vowel and the suffix starts in a vowel, we usually drop the vowel off of the prefix. A significant exception to that is with tri. Tri, you do not drop the I off of that. Triiodide has 2 I's in it. Trioxide has an I before an O. Into O is dinitrogen monoxide. Now, in contrast, if the cation is only 1, we don't use the mon. For example, NO2 is not mon dioxide, it's just nitrogen dioxide, okay? And when you may be familiar with, for example, CO, carbon monoxide. Carbon doesn't have a mon in front of it. So like the first one here, nitrogen monoxide. Oxygen monofluoride, because fluoride starts with an F. Nitrogen trioxide. We don't drop the I when we're working with tri, even if the next one's a vowel. N2O5, dinitrogen pentoxide. We do drop the vowel there. It's not penta, it's just pentoxide. BCl3, what's that called? Trinitrogen hexachloride. P4, what's that called? Be careful. You're probably tempted to say tetraphosphorus. It's just phosphorus. Just go with phosphorus. We're only going to use these prefixes when we need to distinguish between other things, and the most common form of phosphorus is P4. But P4O10 is tetraphosphorus decoxide. B2P3 is diboron triphosphide. CL2O is dichlorine monoxide. And the last one is just chlorine. All right. And if you're going the other way around, this is the easy way. That was climbing uphill. This is going down. Now you just read the numbers off there and put them into the formula. Carbon tetrachloride, also known as carbon tet. Carbon has no prefix, so we assume 1. Tetrachloride means 4 chlorides, CCl4. Dioxygen monofluoride, 2 oxygens on a single F. Nitrogen dioxide, a single nitrogen on 2 oxygens. Diphosphorus nonachloride. Okay, so that's di is 2, so phosphorus P2, and then chloride 9. Hexabromine dinitride. And like I said, you just kind of read off the numbers and you should be good. All right. And yeah, that last one, nitrogen oxide, that should have been nitrogen monoxide. Remember, we do put the mon when it's the second one. Okay. So that's naming compounds. That's naming elements and the ions made of them. That's naming binary compounds where the metals have variable charges. Also, when you have covalent binary compounds, we're halfway home. We still need to talk about polyatomic ions and the compounds that are made of them. And we still need to talk about acids.